I don't have it on there.
It actually looks like
Well, it's optional, Jake.
but it's not real.
I know. For today and tomorrow. Focus your attention up here. We are going to learn the chain rule today. So far with derivatives. Chapter 3 is all on rules for differentiation, rules for finding derivatives of different types of functions. So we've gone through how to find the derivative of a polynomial, how to find the derivative of e to the x, how to find the derivative of a product, of a quotient, and then derivatives of trig functions. Today, the chain rule is used for finding the derivative of the composition of functions. So if you have a function in the form f of g of x, the chain rule is the rule that you use to find the derivative. Similar to product and quotient rules, I'd say one of the toughest things about chain rule is just being able to recognize when you need it. You really have to pay attention to, okay, to find the derivative of this, I need to use the chain rule. Just like looking at, you have a product, don't just take the derivative of each term and multiply them, you have a product rule. So it's practice not only learning the chain rule, but then in general knowing when to use it. And how I have set this up is I am going to go through 3 examples explaining how to use the chain rule before I formally define it to you. Because I think with this type of rule, it's kind of easier to see how to use it right away versus if I just read the definition. I mean, it's on your sheet, you could look at it, but if I just read it, it might not make a lot of sense. So 1, 2, and 3, these examples are all very similar. So you can recognize all 3 of these as composite functions. We have a quantity raised to the 5th power for number 1, and then just different powers for 2 and 3. So how I want to discuss this for how to find f prime of x is, first of all, if I asked you, I'm just going to say g of x over here, say we just had x to the 5th power. So we have a quantity to the 5th power, but say we just had x to the 5th power. What would the derivative be? 5x to the 4th. Okay, the difference here is, so the derivative rules we've learned are still going to apply. We're still going to use this power rule that we learned. The difference, though, is we have a quantity raised to the 5th power, not just x to the 5th power. So that's your clue that you need the chain rule when it's more than just x raised to a power, in this case, for the power rule. So, how you do this? We are still using this rule, like I said, so there's kind of 2 parts to the derivative. The first part to the derivative is taking the derivative of what I usually call the outside function, and that would be the fact that you have something to the 5th power. The 5th power is the outside function. So to take the derivative, right now we have something to the 5th power. We're going to write it in this form, but we don't just have x, we have that quantity. So the derivative of the outside would be, using the power rule, 5 times, we keep the quantity we have the same, 2x plus 3, to the 4th power. So that's using the power rule, derivative of the outside. However, because it's a composite function, we also need to then find the derivative of the inside function and multiply the derivative of the outside by the derivative of the inside. So we multiply this by the derivative of 2x plus 3, which is 2. Okay, so setting this up, I've had students in the past, rather than calling it the chain rule, I mean, you need to know that's what it's called formally. They call it the inside-outside rule, or the outside-inside rule, because you have the derivative of the outside, derivative of the inside. So this piece would be the derivative of the outside, and then the 2 is the derivative of the inside. And then you just simplify it, whatever that means with your function. So in this case, the 5 and this 2 here, we could multiply those to be 10. So we could write this as f prime of x is 10 times the quantity 2x plus 3 to the 4th power. And that would be the derivative of that function. So as we work through these, like I said, I have 3 examples that are all kind of similar before formally defining the chain rule, but it's the derivative of the outside, and you leave your inside function as is, and then multiply by the derivative of the inside. So if we look at 2, say I wanted to find g prime. I have a quantity to the 8th. Like I said, 1, 2, and 3 are all set up very similarly. I take the derivative of the outside, so I keep the x squared plus 2x plus 3, I keep that the same. The derivative of the outside is something to the 8th power, so it would be 8 times that quantity to the 7th power, and then I have to multiply that by the derivative of the inside, and what's the derivative of x squared plus 2x plus 3? 2x plus 2. Okay, so this, in terms of simplifying, I would probably just leave this as is, leave it in the factored form. You could, I mean, if you wanted to distribute the 8 to the 2x plus 2, it's not really necessary. You could, if you wanted to, the 2x plus 2, you could factor out a 2. So I guess I would write that. If I factored out the 2 would get multiplied by the 8. So it'd be 16 quantity x squared plus 2x plus 3 to the 7th, and then this quantity would become x plus 1. So that would be a way to further simplify it. But remember, leaving your answer like this that I had originally is fine. This is probably how they would have it listed in terms of like multiple choice options. They would simplify it. So knowing how to simplify it is important, but I would not take off if you left the answer this way. Okay, so just do 3 quickly following that same method, and I don't know that I need to walk around, but just answer it without me, and then we can all check and make sure we have the same thing. All right, I am going to show, I didn't do anything to simplify this, I just left it with the first step so you could at least check that. So -7 times that quantity to the -8th power, make sure you're subtracting 1, times the inside derivative is 3x squared plus 4x plus 2x to the -3rd. How did I get what? The derivative of negative or minus x to the -2nd. The -2 times the negative would become +2, and then you take 1 away from the exponent to get -3. Okay, any questions? That's the idea of chain rule. Okay, so this is how it's formally written. As long as f and g are both differentiable, meaning you're able to take the derivative of both, then they're just defining a composite function f of g of x. Then this is the notation for the derivative. So it's written as f prime of g of x times g prime of x. So this here just means, I left some space if you want to write down what it means, but this means the derivative of the outside, leaving the inside the same, what we just did. So that's how that's written. So f prime of g of x, the inside doesn't change, just like we had done in examples 1, 2, and 3, but you're taking the derivative of your outer function, and then you multiply by the derivative of the inside, which is the g prime of x. So understanding what that means. So if you can identify the outside and the inside functions, that's helpful if you think of it that way in applying the chain rule. All right, I'm also going to show you how this is written in Leibniz notation. The Leibniz notation I find helpful in understanding why this rule actually works. So I'm not going through a proof with you, but like I said, the Leibniz notation maybe can help you understand why it's the derivative of the outside times the derivative of the inside. So say you have your function written as y equals f of g of x. And I am going to replace, now I typically don't like when they use u, but I'll use what they use in the book because some students can't handle it. Okay, so u equals g of x. I'm going to replace g of x with u. This is how they show it in the definition, yes. So then I can rewrite y as f of u. Oh, right. Okay. So then the Leibniz notation, if I take the derivative of y, so y is now a function of u. So in Leibniz notation, it would be dy du, the derivative of y with respect to u. That would be f prime of u. So the dy du would be the Leibniz notation for that derivative. This is the derivative of the outside. And then for the inside, u is a function of x. So in Leibniz notation, the derivative would be du dx, derivative of u with respect to x. That would be g prime of x, or the Leibniz notation for g prime of x. And this is the derivative of the inside. So overall, if we are trying in our original problem, because y originally is a function of x, f of g of x. So by trying to find the derivative, you are trying to find dy dx. We are trying to find dy dx, and if we apply our chain rule, it's derivative of the outside times the derivative of the inside. So it would be outside is dy du times inside is du dx. And then if you just glance at that, hopefully then it makes sense why the derivative of the outside times the inside equals dy dx. If you think of these as fractions cross-canceling, you would get dy dx. Well, either way, dy over dx means the derivative specifically of y with respect to x. If you just see d dx, something has to follow it because it means you're taking the derivative with respect to x of whatever is after it. that make sense? All right, so Labney's notation, you do. You may not have to write it that way, but questions will give it to you that way. So if you don't recognize it, then you won't know how to answer the question. Okay, here are more examples that may or may not look like the first three we went through. Okay, so yes, for number 4, f of x is the square root of x squared plus 1. This you can rewrite as x squared plus 1 to the 1/2 power. Now it does look like examples 1, 2, and 3. The derivative would be derivative of the outside, leaving the inside the same, is 1/2 times x squared plus 1 to the negative 1/2 times, what's the derivative of the inside?
2x.
2x. All right, I would simplify this. The 1/2 and the 2 can be multiplied. So you could write it as x times the quantity x squared plus 1 to the negative 1/2. If you did not want to leave a negative rational exponent in your answer, you could write this as x over the square root of x squared plus 1. You do not need to simplify the radical. The radical is simplified. Or do you mean with it being in the denominator? That doesn't apply in calculus. Yeah, you don't need to rationalize denominators. This is probably the answer choice you would see in a multiple choice question. All right, so needing to know how to simplify. Okay, so then for 5. So this one is not written like 1, 2, 3, or 4. We have sine of x to the 4th plus 1. So again, here is your indication that you need the chain rule. We have a derivative rule for sine of x. If you have sine of a quantity, that is now chain rule. So if it's anything more than just x or more than just a variable, that's it, you need the chain rule. So here your outside function is sine of a quantity. Your inside function is x to the 4th plus 1. So to find y prime, you find the derivative of the outside function, leave the inside the same. So what's the derivative of sine?
Cosine.
Cosine. So it would be cosine of, and you leave x to the 4th plus 1. Okay, that's the outside. Then you multiply by the derivative of x to the 4th plus 1. 4x cubed. Okay, that's your derivative. The only thing, if you were looking to simplify or rewrite, I would probably rewrite the 4x cubed in front. You cannot distribute it. Just make sure you understand that. This is inside the cosine function. You can't factor out anything. This is not the class where you make up your own rules. Okay, so I would probably write it this way. Okay, questions on 5? Okay, I would actually, well, we'll do this. For 6 and 7, these kind of go together, kind of not. Not meaning they're not the exact same, but I put them both on here on purpose. So y equals sine of x squared. What is the inside function for number 6? The x squared. So there's not parentheses, but you could put parentheses around the x squared. Okay? What about for 7?
Oh, shoot. That's a tricky one.
This is sine of x squared. So sine of x is your inside function. So I would like you to find the derivative for 6 and 7. I just want you to try these without me leading you through them. You could look ahead at 8 and 9 as well if you'd like. But 6 and 7 will for sure make sure we understand before we move on. So I helped you identify what's the inside for both. Yes.
No.
You take the derivative, right?
Yep.
I know, I'm not on your level, I'm on your class.
Oh, shoot.
I didn't think it was gonna query like that.
Oh, shoot.
Is that his only pencil? Is it? Bro, don't get rid of it.
Alright, I want to be quick with this. Some of you already have 8 and 9 as well. Double check 6 and 7. For 7, Kai had asked, could you also write this as sine of x times sine of x and use the product rule? Yes, you can. You should get the same thing.
Yeah, I got it.
Okay, 8 and 9 are very similar because they both involve e. So Here again, why are you using chain rule? Because you don't just have e to the x. You have e to something else. E to the sine of x. E to the 4x cubed. What is the derivative of e to the x? E to the x. So with chain rule, the derivative of the outside is the same function because e to the x is the derivative of itself. So the derivative of the outside for a would still be e to the sine of x. Then you have to multiply it by the derivative of sine. So that would be cosine of x. Okay, so that would be your derivative if you wanted to write cosine of x in front. There's not a great way to write that, I guess. But then, no, because this is an exponential function, not a power function. Because your variable is an exponent. So then 9 is very similar. Anybody have the final answer for 9? Yes. So here's your derivative of your outside. Derivative of the inside is 12x squared. I would probably write that one in front. All right, so we have time today. That's all the examples I have for you. So you have time to work on the practice. You should work on this. The only way to recognize chain rule is to practice it. And since you have over 15 minutes, you have almost 20 minutes, you should be working on this.
Yeah, that's over.